Hello dear GATE aspirants, welcome to Veda GATE Academy. In this video, we are going to study about control system stability. So in this video, primarily we are going to study about the response of the system, response of dynamic system. Dynamic system means the system which is going to have at least one energy storage element, dynamic system. And after that, the basic definition of stability in time domain, basic understanding or definition, whatever it is, basic understanding. This is very important, please. This is very important. Basic understanding in time domain of the stability is very important. Basic understanding of the stability in time domain. In time domain. Basic understanding of stability in time domain. Then we are going to extend this time domain understanding into frequency domain. We know frequency domain is easy in many aspects. We already seen in the previous classes. So extending stability understanding, extending stability understanding to S domain, stability understanding to S domain, understanding, yes, to S domain. In S domain, again, we have few more things to do. That is basic way of finding stability by using S domain. The basic way to find stability in S domain. What is the basic way to find stability in S domain? Finding poles by solving the characteristic equation. That is finding poles location in S plane by solving characteristic equation. But as the characteristic equation order increases, it is very difficult to solve the characteristic equation. Therefore, we are going for RH criteria, Routh-Hurwitz criteria, which gives the stability without solving the characteristic equation. So the next topic in this is RH criteria, a tabular method of finding stability without solving the characteristic equation. RH criteria. Now in RH criteria, we have some difficulties. All those things will come under RH criteria. Yes, there are some shortcuts in RH criteria. Without solving, means without even tabular formation of this RH criteria, just by looking at the question, we are able to say whether the system is stable or not for third order and fourth order. Yes, for third order and fourth order. The shortcuts what I'm going to give have some limitations. Those limitations also we will discuss. Importantly in this, if you want to understand the complete picture of stability here, in basic understanding of stability in time domain, this is very important. Some of you know entire stability discussion is going to depend on poles location. Poles. Completely stability discussion is done by using poles location. Why poles only are taken into consideration while discussing stability? For this, we are going to give some good explanation. The understanding in time domain, understanding the stability in time domain is very, very important. Before that, we need to understand this one, that is total response of a dynamic system. Let us take that concept, that is total response of a dynamic system. Yes, total response of a dynamic system. Yes, total response is equal to, every system is going to have two responses, natural response and forced response. In fact, every dynamic system, please. For static systems, there is no natural response. It is going to have only forced response. So total response is equals to natural response plus forced response. See, I think you solved differential equations in mathematics. Every differential equation is going to have two solutions. One is a complementary function, another one is particular integral. While you are finding complementary function, you made input equal to 0. While finding particular integral, you taken the input into consideration. Yes, Here we are going to see that is a mathematical way of understanding total response or solution of a differential equation. Here we are going to understand in physical way, please. A dynamic system is going to have natural response plus forced response. For understanding this, I'm going to take up two examples. The first example is very informal example, just for the understanding purpose I'm taking. But the second example, what I'm going to take is a technical example from network analysis. Please follow both, but second one is more important for us than the first one. The first example is taken only for understanding this total response, natural response, and forced response. Suppose, take your classroom. In your classroom, suppose if your classroom faculty or teacher or professor, whoever is there, then a student will sit in the class. His behavior is going to contain two parts. That is, by keeping the faculty member in mind, he will sit calmly. But when the faculty member is not in eye contact with that student, then he is going to behave in his own way. Means when when the faculty is looking at the student will behave in one way. When the faculty member is not looking at the student will behave in another way. Means here a student is going to have two behaviors. One is forceful behavior due to the faculty, another is his own behavior. We know very well his own behavior is not required in classroom when faculty member is there. Yes, according to the classroom regulations, he need to move according to those regulations. So a student is going to have two behavior. One is his natural behavior, student's natural behavior. Another one is forceful behavior, which he got due to the faculty member. In the same way, every system is going to have two responses. One is natural response, another one is a forced response. What is forced response? So this is the response. This is the response which is due to the input given, or this is the response which follows input. So instead of due to the input, we will say like this: this is the part of response which follows input. What does it mean? Suppose if my input is a step input, this is step input, say some 5. Now the output, this forced response, is also in step manner. Maybe 5, may not be 5. So magnitude is not important for us, but this is following. This forced response will follow the input. Means I'll take we will take more clarity here. What is a natural response? Natural response is due to system behavior or system conditions. Let us see by taking an example. Then we will understand about this natural and forced responses. But one thing we need to remember permanently, that is, forced response means that exactly follows input. If my input is step, forced response is also step. Magnitudes may be different, please. If my input is ramp, forced response is also ramp. If my input is parabolic, forced response is also parabolic. But natural response will never follow input. Whatever may be your input, this natural response is going to have its own format. Then you might raise the question, sir, on what this natural response behavior depends? On system parameters. Yes, this natural response depends on system. That is called as system response. In fact, system response. What we want, I always want this forced response. I do not want this natural response. Why? Because suppose if you take one circuit, we are giving some input to the circuit such that output is following input. I want this one, I do not want this one. But can we make this one not to be there in the system? No, we cannot make directly. We want this one to reduce to 0. We do not want natural response, but the name itself is saying naturally that response is coming. If that natural response is decreasing, or when compared to this forced response, this natural response is very, very less, that system is said to be a stable system. Very, very less means tending towards 0. We always want forced response. We are giving some input to the system such that that system is going to follow the input, or the output what we are getting must follow the input. Among these two responses, which response is following the input that is given by us? Forced response. But the response, this natural response, is not following the input. Forced response is having many names. In the same way, natural response is also having many names. All those names we'll see after looking at the technical example. I'm going to take this example, understand this example please. Yes, this is the example what I'm taking. This is the RC network. I'm taking series RC network, series RC network. So this is resistance, this is capacitance. Yes, resistance and capacitance. Here, let's connect a DC voltage source V. V is DC voltage source. We connected to this circuit. Now, the current in this circuit, I am taking it as I of t. Current in the circuit, we are taking it as I of t. Let's write its KVL. Find both the responses, natural response and forced response. Or first of all, let's find total response. In that, what is the natural response? What is the forced response? Let's observe. Now, if I write KVL minus V plus I of t into R plus 1 by C integral I of t dt is equal to 0. That is the KVL. First order differential we are going to get. One integration we have, therefore one S term we are going to get. Therefore this system, first order system, we all know very well from first chapter where we learned about the order of the system. Now I'll apply Laplace transform. I will apply Laplace transform technique. You know very well why we are discussing Laplace transforms, or why we are discussing entire control system in Laplace domain or S domain. So this is going to become minus V by S, or first step minus V by S plus I of S into R, I of S into R plus 1 by Cs into I of S. 1 by Cs into I of S is equal to 0. So from this, I of S is equal to what we are going to get? V by S by R plus 1 by Cs is the current what we are getting. I want voltage across capacitor. I want voltage across capacitor Vc of t. Now for that, first of all, I need to find Vc of S. Vc of S is equal to what? Capacitance. You know, in S domain, Ohm's law, voltage division, current division are directly applicable. What is the voltage across this capacitor in S domain? Vc of S is equal to 1 by Cs. Capacitance in S domain will be 1 by Cs into I of S, because I can apply directly Ohm's law. Voltage is equal to current into impedance, 1 by Cs into Ohms. Now let me simplify it, please. Let me simplify it carefully. Now observe here. What is this? Vc of S is equals to 1 by Cs into V by S by SCR plus 1 by Cs. SCR plus 1 by C. This Cs gone. Vc of S is equals to V by S by, let's take RC common. What we have? S plus 1 by RC. S plus 1 by RC we got. Then apply inverse Laplace transform to get the response, please. Apply inverse Laplace transform, because we always want the answer in time domain. Our problem is in time domain. We want the answer in time domain, but the medium of solution is frequency domain due to some advantages. These advantages we already discussed in the starting chapters. Now come on. Vc of S is equals to V by RC into 1 by S into S plus 1 by RC. Now we have learned how to find partial fractions very easily. Direct method we learn. Anyhow, we'll revise once again here how to find partial fractions very easily. Now, as we have two terms, we'll be writing like this. Two terms we'll be writing like this. If you want this constant, if you want this constant, yeah, we want this constant. For this one, what to do? Make its denominator equal to 0. Yes, S is equal to 0. Now in this expression, you close it. In the remaining expression, you put S is equal to 0. Once again, I'll be taking this. If you want this A, if you want that A, we are not going with that basic method AB plus BS like that. We are not going to do all those things. If I want this A, if I want that A, yes, we want this term, please. For that, make its denominator equal to 0 first. I got S is equal to 0. In this expression, as V by RC is outside, we are not going to touch it. In this expression, you close this, and in the remaining expression, you put S is equal to 0. How much you got, ma? We got RC. We got RC. Yes. Now here, if we want this one, then what to do? Make this equal to 0. What we get? S is equals to minus 1 by RC. In that expression, or the expression what we have here also we have the expression. This V and RC we kept outside. In the remaining expression, remove this one. In the remaining, what we have? 1 by S. V by RC is outside. Yes, outside. where we want to substitute, we want to get this one, therefore we need to close this one. In this we need to substitute that one. What we have, s is equal to minus 1 by rc. If we keep minus 1 by rc, that is going to become like this. Now rc will get cancelled once we take outside. Yes, rc, that method is called as direct inspection method of finding or partial fractions, please. Direct inspection method of finding partial fractions. Very easy. By taking one more example, I'll illustrate that, no problem. So vc of s is equals to v into 1 by s minus of 1 by s plus 1 by rc. S plus 1 by rc. Observe it, observe it. We got vc of s. From this we are going to get vc of t. From this we are going to get vc of t. vc of t is equals to v is v. Inverse Laplace of 1 by s is what, u of t. Inverse Laplace of 1 by s is u of t. That's why I told you in the starting classes, Laplace and inverse Laplace transforms are very, very important if you want to understand control systems. Minus, what is inverse Laplace transform? E power minus t by rc into u of t. E power minus t by rc into u of t. Now, vc of t is equals to v into u of t minus of v into e power minus t by rc into u of t. Yes, observe this expression completely. Yes, observe this expression. Now, what is the value of u of t? U of t value is 1 for after t is equal to 0. After t is equal to 0, u of t is equal to 1. Then let's write vc of t is equals to v minus v into e power minus t by rc. Let me draw the system what we taken once again here. Let me draw the system what we taken once again here. Yes, sorry, we taken capacitor, not inductor, please. Capacitor we taken. Now observe this one carefully. This is R, this is C. This is R, this is C. This is the voltage source, DC voltage source we taken. Now the voltage across capacitor is Vc of t. Vc of t. Current in the circuit we taken as a I of t. Observe here, ma. What is the input given by me? Input is, what is the input given by me? V. What is this one, please? This part of response is, that is also V. I told you, need not to be necessarily V. It may be V by 2 or V by 3 or V by 4, some K into V. But here, fortunately or unfortunately, that is directly V. So this part of output is exactly following input here. Here exactly input. This response is called as, I told you, the response which follows input is called as forced response. Yes, this response is called as what, ma? Forced response. But if you observe, this part of response is exponentially decreasing. We given DC source, DC input, but this response is exponentially decreasing like this. This part of response is not following input. Please observe carefully. At t is equal to 0, its value is v. As time t tends to infinity, it is going to become equal to 0. It is decreasing with respect to time. The part of response which does not follow input is called as natural response. The part of output which does not follow input is called as what, ma? Natural response. Natural response. Some people, even some faculties, don't know the difference between natural response and transient response. Some people will say that natural response and transient response both are same. No, please. Natural response and transient response are very much different. In the same way, forced response and steady state response, they will say both are same. No, please. A lot of difference is there between forced response and steady state response, natural response, and this transient response. Transient response and natural response both are not same. For your kind information, some faculties also don't know about this one. Please be careful what you are learning. All these questions are many a times asked in interviews and sometimes in gate examinations, sometimes in other competitive examinations. So please understand well. We will see after some time the difference between natural response and transient response and forced response and steady state response. Let us see after some time. First, let's concentrate on this classification of responses. Yes, we have two responses, natural response and forced response. So Vc of t is equals to minus v into e power minus t by rc is natural response, plus v is a steady state response. In this example, we got exactly the input what we given, but it may be into k may be any number less than 1. So please every dynamic system is going to have two responses, natural response, forced response. Now here the origin for stability will start here. The origin for stability will start here. But before that, let me understand few more things. Here, let's find the transfer function of the system. Let's find the transfer function of the system. You know very well how to find the transfer function. We'll draw the circuit once again and we'll find the transfer function. Yes, for finding transfer function, our circuit must be in which domain? S domain. Our circuit must be in S domain. So this is a Vi of S I will take. Vi of S. This is R. But the capacitance in S domain will be 1 by Cs. This is ohms. Its units are also ohms. 1 by Cs units are ohms. What is the output we taken? The output what we taken was Vc of S. Now what is the transfer function? Laplace transform of output by Laplace transform of input. Now what is the output Vc of S? Vc of S is equals to Vi of S into 1 by Cs output impedance by total impedance. Output impedance by total impedance. From that, Vc of S by Vi of S is equal to what? 1 by SCR plus 1 we got. So this is the transfer function. Transfer function. Observe it carefully. So this is the transfer function. Now, what is the characteristic equation? Characteristic equation is equal to SCR plus 1 equal to 0. Now, where the closed loop pole is located? Closed loop poles are roots of the characteristic equation, that is S is equal to minus 1 by RC. Observe this one carefully and let's write the forced response and natural response once again. That is Vc of t is equal to what? V minus, this is forced response, V into e power minus t by RC. T into that pole. Yes, minus 1 by RC is what? Pole. Means observe here carefully. Here many statements we are going to understand. We always want forced response to remain in the system. See, natural response is means we can't we can't stop the natural response. Means we can't deny it. We may reduce it, but we can't deny it. It will be there in the system. If that natural response is decreasing with respect to time, see, if you see a student who is not good at discipline at childhood, when he is growing up, he will learn the discipline that we require. But if he is having his natural childhood behavior forever, then definitely he is unstable. Means we always want forced response. We don't want natural response. Means this is the natural response that depends on the pole. First point what we need to understand is we want always forced response to remain in the system. We do not want natural response. This is the first point. Second point is we cannot deny natural response. Why? Because every system is going to have natural response. Every person is going to have some disadvantages. But if the advantages are very high when compared to disadvantages, then he is a stable person. If the disadvantages are more when compared to advantages, he is an unstable person. In the same way, this natural response, if this natural response is decreasing to zero as t tends to infinity, this is how in the same way. Means if as a person growing up in the age, if his all bad habits or disadvantages are reduced, then he is going to be stable. But if those bad habits or disadvantages are increasing as his age is progressing, he is an unstable person. Yes or not? Yes. So if the natural response, this is natural response which we don't want, this is the forced response which we are we want very much. We want that forced response to be there in our system. If the natural response of the system is decreased to zero as time t tends to infinity, then the system is said to be what is said to be said to be stable. Then that system is said to be stable. That is called a stable system. So this is the physical way of understanding stability. But if you look at the expression what we got, we'll write the expression once again, please. We'll write the expression once again. That is Vc of t is equals to V minus V into e power minus t into pole. What is the pole we got? Where pole is equal to minus 1 by RC. Sorry, pole is equal to not minus t into place. We wrote wrongly. This is because pole itself is minus. Pole itself is minus. Yes, that minus is not there. V minus V into e power t into pole. Now, if I'll take up like this. If pole magnitude is positive, then what happens? Please do not depend on this example. Anyhow, in this example, pole value itself is minus 1 by RC. Pole value itself is minus 1 by RC. No issues here. Yeah, I'll tell you. I'll explain you very clearly. Observe. As here pole value is already negative, what happens? E power of a negative into t. As t is increasing, this e power of negative will decrease to 0 as time t tends to infinity. As time t is tending towards infinity, why? Because e power minus some x are not required to take x, See, e power some negative into t. If this t is infinity, negative into infinity will be minus infinity. How much it is? E power minus infinity, that is equal to 1 by e power infinity, that is equal to 1 by infinity, that is equal to 0. Means whether this natural response is decreasing to 0 or not. This natural response decreasing to 0 or not will be decided, yes ma, will be decided by poles. That too, real part of the pole. We are going to take some examples. In that example, I'm going to clearly mention you only real part is matter for us, not imaginary part. Now here we have only one pole. One pole means definitely it is going to be real pole. That's why in this example, no matter, here pole is minus 1 by RC. See, V minus V into e power t into minus 1 by RC. If this t is increasing, this V into e power minus t by RC will decrease towards 0. We are going to have only Vc of t, that is equal to V. We are left with only forced response. That is our requirement. I always want, not only me, any system want practically the output to follow the input. Means we want only forced response to remain. We do not want natural response to dominate the forced response, please. We always want the natural response to die to 0, please. Except in some applications. Some applications will run only on natural response. What are those applications which always want natural response? We'll see it later. In the last closing of this stability topic, please. So Vc of t is equal to only forced response as t tends to infinity. But if you design a system in such a way that, yeah, we have a system like this, observe. So some Vc of t is equal to V into e power minus V into e power minus t by Rc. Anyhow, R is positive, C is positive, therefore T by RC is always positive, minus T by RC is always negative, therefore no problem here. But if I take one example, let me take one example, please. From that example, I'll explain. Transfer function is equal to, what is transfer function? Output by input, or output generally in control systems, we'll take output as C and input as R. Yeah, that is our denotation. In this initial class, we've seen C of S by R of S is equal to some example transfer function. I'm taking here some example transfer function. 1 by S minus 2 is the example what I taken. Now from this, I want to find the output. What is output? C of S is equal to input into transfer function. Input into, what is the transfer function? 1 by S minus 2. Let's imagine the input what we are taking this step. If input in time domain is equal to unit step, then what is R of S? R of S is equals to how much? 1 by S. Substitute there. C of S is equals to 1 by S into S minus 2. 1 by S into S minus 2. Observe 1 by S into S minus 2. Now I want to find C of t. For that, we need to find inverse Laplace. For that, we need to apply inverse Laplace. Let's find partial fractions first. I told you that previously. We'll understand this finding partial fractions with the direct inspection method. What is that? I'll tell you. If you want this numerator, first numerator, first make this equal to 0, S is equal to 0, then substitute this one and this by closing this one. Those numerator you want to find, close that. In the remaining, you substitute that S is equal to 0. What you got? How much you got? Minus 1 by 2. Yes, done. Now, if you want its numerator, first of all make this equal to 0, S minus 2 equal to 0. How much we got? S is equal to 2. Take this, substitute in this one by closing this S minus 2. Then how much you are going to get? 1 by 2. We got 1 by 2. This is direct inspection method, please. Direct inspection method of finding partial fractions. Now let's write C of t. C of t will be C of t equal to minus 1 by 2 take outside. 1 by s is what ma? U of t. Yes, plus 1 by 2 be taken common, not 1 by 2. Let's take let's remain it as it is, minus 1 by 2 into u of t, yes, plus 1 by 2 into e power 2t into u of t. You must be very good in partial fractions, Laplace and inverse Laplace transforms. Then only you can understand control systems. What is this? This is forced response. Sir, how do you know that it is forced response? Observe here, ma. Observe here. What is the input taken by us? The input is step. Input is taken by us is what? Step. We taken step. We are getting in the output also step form. I told you magnitude may be any value, not a matter. But here also you might be thinking, sir, this is following. No, this is not complete answer, please. Complete signal. E power 2t is the main signal. This u of t says that the response is started after t is equal to 0. These things we already seen in the starting classes. E power 2t is the signal. U of t will says that e power 2t is started at a t is equal to 0. But here the signal what we have itself is u of t. Therefore, here this is the forced response. Why? Because the input is step, output is also step. It may be negative in step, negative in magnitude, or positive in magnitude, not a matter. But here what we got forced response e power 1 by 2 into e power 2t into u of t. Anyhow, that u of t value is 1. Need not to write that u of t value. U of t value is 1. If you observe carefully, as time t tends to infinity, what is happening now? As t is tending towards infinity, e power 1 by 2 into e power 2 into infinity will be what? Infinity. Natural response is increasing to infinity, which we do not want. Increasing to infinity, which we do not want. This system is said to be stable or unstable? Unstable. So why it is unstable? What is the reason for this? Why? Because here natural response is tending towards infinity, then that is said to be unstable. What is the reason for this? Let's backtrack it. Let's backtrack by doing like this. Yes, what is a pole? Pole is s is equal to 2. Pole is s is equal to pole is in the RHP or LHP. Pole is in right half of its plane. From this we need to understand that if pole is there in the right half of its plane, the pole value will appear in the exponential power. If the pole is positive, exponential power is also positive. Exponential power is positive. As t tends to infinity, what happens? That value also will become infinity. Then system will be unstable. So this is the reason why poles are very important in understanding the stability concept. So from this, what we understood from this concept, if pole real part is in the right of its plane or pole real part is positive, then that system is unstable. There are so many points to add to that, please. That is not the final statement. That is not the final statement. So from here, we understood that poles are going to play an important role in understanding stability. Location of poles is going to decide whether a system is stable or not. Therefore, I want to find all the poles of a given system and its location. We need to find all the poles and poles location in the S-plane. If all the poles are in left half of S-plane, left half of S-plane means if you take this as S-plane, this is sigma, this is j omega, this is the origin. All left values will be negative values, all right values will be positive values. If all poles are in left half of S-plane, then what we are going to get, all exponentials negative, all exponentials are negative, t tends to infinity, all exponential will become equal to 0. But if any one pole is in the right half of S-plane, remaining all are negative means remaining all poles are in left of S-plane, remaining all are in left means those exponential will be negative, but one exponential is positive means what happens, that will become infinity. Infinity plus anything will be what? Infinity. Means one pole in the right half of S-plane is enough to make the system unstable. There are many points to understand about instability or stability is not yet completed. One statement we are looking at, we need to discuss about the imaginary axis also. This is just an introduction. So location of poles in S-plane is very important in understanding stability. If a characteristic equation is given, definitely we need to find poles from that. Then only we are able to find the stability. Observe here, ma. Observe. Come on here. So we understood the difference between natural response and forced response. A natural response is due to what? System poles. Natural response is due to what? System poles. Come on. What we got? Vc of t is equal to v minus e power t into pole. In the second example, what we got, c of t is equal to what we got, minus 1 by 2 into u of t plus 1 by 2 into e power 2t into u of t. This 2 is what is the transfer function we taken? The transfer function what we taken is 1 by s minus 2. What is the characteristic equation we got? S minus 2 equal to 0. What is the pole we got? That is s is equal to 2. This 2 is that one place. This is 2. That is this value. Yes. But this 2 is positive. That's why this exponential power is a positive. So the response, natural response, exclusively depends. Means you need to understand in this way, whether natural response is increasing or decreasing will depend on pole's location. So then what is the significance of zeros? Does zeros are not having any significance? Let us see what is the significance of zeros also, because we should not forget about zeros. Zeros are also having some significance which is not very important in the respect of stability, but let's see. See, zeros means transfer function zeros wherever those are present. Stability means whether a system is stable or unstable is not decided by those zeros. The relative stability, there is one term called relative stability. We'll see that relative stability will be decided by a system zeros location. We'll see anyhow. So transfer function is equals to we'll take like this, s plus 1 by s plus 2. This is one transfer function. Let's find some response, please. C by R transfer function can be written as C of s by R of s is equals to, let's take s minus 2 itself. Let's take s minus 2 because our previous example is 1 by s minus 2 without any 0 we take it. Here I had taken a 0. Here I had taken a 0. So let's examine if 0 is there, what happens. So s plus 1 by s minus 2. I want to find see C of s is equal to step 1 by s I am giving. Input is step R of t is equal to u of t, unit step we are taking. 1 by s into s plus 1 by s minus 2. Now I want to find C of t. For that I need to write partial fractions. For that I want to write partial fractions. Observe here. So this is s, this is s minus 2. Put s is equal to 0 in this one. By closing this one, if I put how much I am going to get, minus 1 by 2 we got. Put s is equal to, yes, put s is equal to 2 in this expression. What happens? 3 by 2 we get. We get what? 3 by 2. Put s is equal to 2 by closing this one. How much this is? This is 3. This is 2. Now C of t will be very easy. C of t will be equal to minus 1 by 2 into u of t plus 3 by 2 into e power 2t into u of t. What is the expression we got for the previous transfer function? C of t is equal to minus 1 by 2 into u of t. Yes, put minus 1 by 2 into u of t plus 1 by 2 into e power 2t into u of t. What this is for the transfer function with a 0. We taken a system with without a 0 place, 1 by s minus 2. This is for a transfer function or a system with 0, s plus 1 by s minus 2 we taken. Means what is the only difference between these two? Means poles are same for the previous example and this example, but what is the only change? Zeros got changed. The previous example is not having any 0, but here there is a 0. The only change is this one, 1 by 2 became 3 by 2. That's it. Or this may also change, but here fortunately or unfortunately this is not changed. It does not mean to say that only this is going to change. Means I'll give one statement here. That statement is going to complete this analysis, or that statement is going to remove all your doubts. That is, zeros will affect only coefficients in the response. Means suppose if I got a response C of t is equal to c1 into e power minus 2t into u of t plus c2 into e power minus 3t into u of t plus c3 into u of t. Suppose if this is the response. Now if zeros changes, poles remain same. Suppose we take in a system with some fixed poles, we are continuously changing its zeros. Means for example, we have taken a system like this, 1 by s plus 2 into s plus 3, like this. Now this is one system. Another system, let's take some space. Yeah, we have taken another system like this. We have taken another system, s plus 3 by s plus 4 by s plus 2 into s plus 3. So here poles are fixed, s plus 2, s plus 3, s plus 2, s plus 3, s plus 2, s plus 3. Here there is no 0. Here we take in a 0. Then what happens? Then what happens here is, in this response, this is the response what we got. Suppose say for that system what we taken, then the only change that is going to happen is this c1, c2, c3 will change, but this e power minus 2t, e power minus 3t will remain same as this. Only c1, c2, c3 are going to change. zeros are not having any effect on stability. Means if you take a system with zeros or without zeros, its stability is not going to change. Means whether that system is stable or unstable is not affected. The only thing that is going to change is the coefficients in the response what we are getting here. We will revise the things what we discussed till now. Stability of a system. A system is said to be stable if its natural response is decreasing to zero. Yes, I told you. We always want forced response. We do not want natural response. Forced response is a response which follows input. Forced response magnitude may be equal to input, may not be necessarily need not to be equal to input. Maybe it may be equal to, also not a problem. Natural response is a response which depends on system poles location as plane. Means whether natural response is increasing or decreasing is decided by the location of poles in S plane. If all the poles are in left of S plane, that system is going to have all exponential power negatives. Exponential power negatives into t as time t tends to infinity, e power minus it will become equal to 0. If any one of the pole is located in the right half of S plane, then exponential power positive we are going to get. As t tends to infinity, e power infinity will be infinity, which is making the natural response to increase without any bounds by with it increase to infinity without any bounds. Means natural response is dominating when compared to forced response. Take one simple example. You are on a bike, you are giving input to the bike is moving according to your command, then no problem. But if the bike started its own behavior, then what happens? You may fell down from the bike. If the bike is following your input command, that is a stable bike. If the bike is not following your input command, we can say that it is unstable. See, bike is going to have forced response. What is the forced response? You are asking the bike to move, or you are commanding the bike to move in particular direction, that is forced response. Natural response is the bike is some small vibrations or many things. Those are not required for us. We want always those natural response of the bike to be very very less or zero. Practically it is not possible to get exactly zero, but if the forced response is very high when compared to natural response, suppose very simply from mathematics, 10 to the power of 6 plus zero point 0.1 approximately can be written as 10 to the power of 6, or sometimes exactly also we can write 10 to the power of 6. Why? Because this 0.1 is not going to affect. If this is forced response, if this is natural response, in this case also I can say that system is stable. Why? Because the natural response magnitude is very very less. So here always we want a forced response. We do not want natural response to increase. Natural response should decrease to 0. Now finally, the definition of stable system is if the natural response of a system is decreasing to 0 as time t tends to infinity. Time t tends to infinity means we are not going to wait up to infinity. Practically we will wait up to only for 5 time constants. You know it very well from network theory part or electric circuit part. Okay, so if the natural response is decreasing to 0 as time t tends to infinity, then that system is said to be stable system. If the natural response is increasing to infinity without bounds, then that system is said to be unstable system. We have one more classification, that is marginally stable system. We need to discuss that marginally stable system also. Marginally stable system is also called as marginally unstable. Means that is 50% stable, 50% unstable. What does it exactly mean? Does that type of systems, means marginally stable systems, practically will exist or not? That also we are going to see. This is the basic way of understanding, or time domain way of understanding stability. How to extend this one to frequency domain? In time domain we are discussing about natural response and forced response. In the discussion of stability in frequency domain, we will discuss about exclusively only poles location, because natural response depends on poles location. We already seen many times. So in frequency domain discussion of stability, we are not going to discuss about natural response. We concentrate only on poles. So system stability depends upon poles location in S plane. Now if we take a characteristic equation, yeah, come on here. If we take a characteristic equation like this, characteristic equation is equals to s square plus 2s plus 1 is equal to 0. We want to know whether that system is stable or unstable. What to do? Solve this characteristic equation. We will be getting two roots. If those two roots are in left of S plane, we can say that it is stable. Otherwise, it is unstable. Suppose if I have a characteristic equation like this, s cube plus 3s square plus 2s plus 1 is equal to 0. We need to solve that third order equation. Then we are going to get three roots. If all the three roots are in left of S plane, then I can say that my system is stable. Now how to solve third order equation? second order equation minus b plus or minus b square minus 2ac by b square minus 4ac by 2a. If you solve, you are going to get two roots. But how to solve third order equation? Some of you will give the idea, sir, take the scientific calculator to solve it. Yes, we can solve. Now, if this is the case, what is that? S power 4 plus 5s cube plus 3s square plus 2s plus 1 is equal to 0. We need to solve fourth order equation. Even scientific calculator also will not give the roots for this one. Then how to find the stability? To overcome this advantage, Routh and Hurwitz's, two scientists, given one tabulation called as a Routh-Hurwitz tabulation for finding stability without actually solving these what you call the characteristic equations. Just this is an introduction, complete understanding of stability. We are left with even marginal stability also. All these things we will be discussing. All these things we will be discussing in the upcoming discussion. In the upcoming discussion, we are going to discuss all these things. So if you go to an interview, if anyone asks you, yeah, this question many times asked in interviews, so that's why I'm stressing here. If anyone asks you why poles only discussed while discussing stability, why only poles are taken into consideration while discussing stability, you know the reason. Stable system means natural response should decrease to 0. Natural response of a system exclusively depends upon system poles location. That's why poles are only considered in the discussion of stability. So this is about the introduction of stability. In the upcoming discussion, we are going to speak about marginal stability, introduction to Routh-Hurwitz criteria. We are not going to enter directly into Routh-Hurwitz criteria. Before we enter into Routh-Hurwitz criteria, some equations, some characteristic equations, just by looking at those equations, we are in a position to say that is stable or unstable, or not stable or unstable. By looking at the characteristic equation, we are able to say whether it is unstable or not. Means we are not giving the guarantee about stability. See, what does it mean exactly? Let me take up an example. Characteristic equation is equal to s cube minus 2s square plus s plus 1 is equal to 0. This one directly I can say it is unstable. This one I can say directly unstable. But whereas this one I can't say whether it is stable or unstable. Here there is a dilemma. It may be stable, maybe unstable. But this is pakka unstable. Sir, how do you know that? There is a sign change between the between the coefficients of the characteristic equation and the between the coefficients of the characteristic equation. Therefore, I can say directly it is unstable. Means all these things, necessary condition, sufficient condition, or establishment, all these things we are going to discuss in the upcoming classes. Thank you.